Dear students, let us now start the second phase of our discussion on interpolation. In our first phase of lectures, we have already discussed what is interpolation, what are interpolating polynomials, and derived a few number of polynomial interpolation formula such as Newton's forward difference formula, Newton's backward difference formula, some formula from Gauss interpolation formula for forward difference and backward difference, for even number of points, for odd number of points, and from them we have derived Stirling formula and Bessel formula. But all these formula are related to the table in which the variable x, that which is called the nodes, are equispaced. For these equispaced nodes, we have Newton's interpolation formula. Forward interpolation formula is applicable when the unknown value of x lies at the beginning of the table. We use Newton's backward interpolation formula when the unknown value of x lies at the end of the table, and we use Stirling and Bessel's formula when x lies in the middle of the table. But let us now go to more general type of interpolation formula. We have given some outline in our first lecture about the general type of interpolation formula known as Lagrange's interpolation formula. In this Lagrange's interpolation formula, the xi's, that is the nodal points, are not necessarily to be equispaced. They may be equally spaced, they may be not equally spaced. In both cases, Lagrange's interpolation formula can be used. How to get this interpolation formula? We suppose that the function y is equal to fx is a function belonging to x0, x1, which is continuously differentiable for n plus 1 times. We construct a polynomial of degree at most n. We have, remember that we have n plus 1 interpolating points. So we construct a polynomial of degree at most n in the form given in phi x. Phi x contains the unknown coefficients a0, a1, a2 up to an, that is total number of unknown coefficients are n plus 1. Now, this n plus 1 unknown coefficients will be determined by satisfying the interpolating condition phi xi, that is yi, I is equal to 0 to n. We should note that xi and yi are the corresponding interpolating points in which no two xi's are equal, that is xi is not equal to yi, xi is not equal to xj for I not equal to j. Then putting in the formula x is equal to x0, x1, x2 up to xn successively in phi x and equating to y0, yi, yn, the coefficients ai can be determined as shown in the table. This is the general formula for an, so that xn becomes this equation. This is the interpolating polynomial due to Lagrange. This is known as the Lagrange's interpolating polynomial, and this can be put in the simple form phi x is equal to summation I is equal to 0 to n Lix into yi, where Lix is given by this expression. This is very important expression. This expression is called Lagrange's fundamental polynomial or Lagrange's function or Lagrange's basic polynomial. Dear students, please keep it in mind that this is very important polynomial which will be used in our future discussions and many other formulation including numerical integration, etc. So please keep it in your memory. Lix can also be written in this form. and in terms of pi x, where pi x is equal to x minus x0 into x minus x1 up to x minus xn, so that pi dash x is the ddx of pi x. Now, what are the advantage of using Lagrange's interpolation formula? Note down that it is much superior to the other interpolating formulas such as the Newton's formula or Stirling or Bessel formula, because it does not require the construction of a difference table. The formula can be applied both for the equispaced formula and also non-equispaced formula, and also in the cases when xi's are not in order. It can be used in any part of the table. This polynomial can be used for finding out the formula for numerical integration. Lagrange's basic polynomial can also be used to derive other formulas too. However, the disadvantage of this Lagrange's interpolation formula is that it requires a lot of computational work. Computational part is really quite laborious. And account for the computational part, we can find that it requires a total number of 3n square plus 5n plus 1 number of arithmetic operation, including addition, subtraction, multiplication and division. So if n is equal to say 10, we require about 350 number of arithmetic operations, including addition, subtraction, multiplication, division. This formula can easily applied to inverse interpolation formula also. This is one of the very advantage of this situation. Let me suggest some problems related to Lagrange's polynomial. Let us begin with the table for x. X is 1.01, 1.05, 1.11. You notice that x is not equally spaced. Let us try to obtain the value of y at x is equal to 1.03, say at x is equal to 1.17 in the middle of the table, or say x is equal to 1.32 at the bottom of the table, and observe that x.32 lies just outside of the given table. In that case, the problem of interpolation is usually called a problem of extrapolation. Answer is given along this problem. So I request you to find the calculations and obtain the result. The result will be accurate up to the last decimal digit. Now, inverse interpolation is a very commonly used problem which can be tackled by using the Lagrange's interpolation formula. In that case, we simply exchange x and y. Simply exchange the independent variable x to y and the dependent variable y to x, and find out the formula from the Lagrange's formula given here. Just interchange x and y, x0 with y0s and xi and yi's with xi's. One problem of inverse interpolation may be like this. From the given table, just we have considered, find the value of x for which y is equal to 1.7751. Then put it into this formula, put the value of xi in the formula, and you will find that y is equal to 1.7751, for which x is equal to 1.15. Given y is equal to 1.7751, we will find that x is equal to 1.15. Another important application of Lagrange's interpolation formula is the root finding of an equation, particularly an algebraic equation. Consider the equation like this: x cube minus 3.5157 x square plus 9.3454x minus 8.55210. We are required to find a real root of this equation. First of all, we assume that fx is a well-behaved function, that is, it is free of oscillations in the neighborhood of the root. And with this assumption, we may conclude that if fxi and xi plus 1, the product of these two quantities be positive or negative, then there will be no root in between them. On the other hand, if fxi multiplied by fxi plus 1 is of negative sign, of opposite sign, then there will be exactly one real root within it. Here we see that at x is equal to 0, fx is negative, at x is equal to 1, fx is negative, but at x is equal to 2, fx is positive. According to our assumption, we conclude that there is no root between 0 and 1, but there is exactly one real root between 1 and 2. After that, we redefine the function. We construct a table like this from x is equal to 1 to x is equal to 2, taking a number of intermediate points. Corresponding values of y is tabled in the following table. Now, x in this table, we may take x to be equally spaced, or we may take x not to be equally spaced, because we will use inverse interpolation formula due to Lagrange's. Use this table for finding the value of x for which y is equal to 0. So we put y is equal to 0, we use the inverse interpolation formula. Putting y is equal to 0, we shall find the value of x, which comes out to be 1.3157. So this is the problem to be computed by you. Please try to do this, because Lagrange's interpolation formula has a good application in finding the roots of an equation. Of course, real root of an equation. Lagrange's interpolation formula is also unique in nature, because if we consider that there is another function, say psi x, will be another Lagrangian polynomial whose degree is less than equal to n, also interpolates the fxi at the same arguments. Then we call gx to be equal to psi x minus phi x, which implies that gx is a polynomial of degree less than equal to n, and gxi is equal to 0 for I is equal to 0 to n. That is, gx is a function of degree less than equal to n, but it vanishes at the n plus 1 distinct points. This is not possible unless gx is identically equal to 0, which implies that psi x and phi x cannot be different. So we have only one phi x, which is the Lagrange's unique interpolation polynomial. Lagrange's polynomial formula is given by y is equal to phi x in the following form, which has already been mentioned in our lecture. The coefficients are Li, given by Li x is equal to pi x by x minus xi into pi dash xi, and observe that if we add Li over I is equal to 0 to n, we will get 1. That is, the sum of the Lagrangian coefficients is always unity. This result can be used for checking the Lagrangian polynomial obtained in our problem. This will be taken as a checking formula. Lagrange's polynomial has some disadvantage also, because in case when n is greater than equal to 5, we shall see that Lagrange's polynomial will get oscillatory form. It oscillates within the limit of our interpolation. We shall now go to another kind of interpolation polynomial, which is known as Newton's divided difference polynomial. Newton's divided difference polynomial. Before going into that, let us now define what is divided difference operator. Let y is equal to fx be a real valued and continuous function of x in a finite region AB, which is called the region of our interest, and let yi is equal to fxi for x is equal to xi, I is equal to 1 to n in the closed interval AB, where xi's are distinct and not necessarily equispaced. We define divided difference of fx for the nodes xi. The first order divided difference is defined in the following manner: f of x1, x2 or rather we should say f of x0 x1 is equal to f of x0 minus f of x1 by x0 minus x1. You can notice that the symbol used f, after that we use third bracket, right, x0 x1. This is the conventionally used in defining the first order difference due to Newton. Similarly, for the other nodes, we have f of x1 x2, which is defined as fx1 minus fx2 by x1 minus x2. You observe that fx1 x2 is also equal to fx2 x1. Similarly, for fxi yi, for fxi minus 1 xi, the result is same if we take fxi xi minus 1 for I is equal to 1 to n. These are the all first order divided difference which is symmetric in nature. The second order divided difference has been defined as f of x0 x1 x2 in this way, and again we find that f of x0 x1 x2 is equal to f of x2 x1 x0. And in general we define the third order divided difference, and actually the nth order divided difference is been defined by f of x0 x1 x2 up to fxn up to xn is defined is like that, which is also equal to f of xn minus 1 like x2 x1 x0. It may be noted that geometrically f of x1 x0 x1 represent the slope of the line segment joining the point x0 fx0 and x1 fx1. The nth order difference can also be written in the summation notation. Let us move to this point, is the summation notation which is written here, and notifying that f x0 x1 is equal to fx0 by x0 minus x1 plus f x1 by x1 minus x0. Thus, divided difference are symmetric with respect to their arguments, and this satisfies all the properties that delta, that is the finite forward difference, satisfies the laws of commutative law, the distributive law, the index law, etc. Divided difference also satisfies all types of properties that the forward difference delta operator satisfies. Divided difference of order n of a function like x to the power n, n being a positive integer, is 1 if we take nth order divided difference of x to the power n, and that of n plus 1th order divided difference of x to the power n, we will get a 0. If we have a polynomial, say px, nth order polynomial given by a0 plus a1x plus a2x square plus an x to the power n. ai's are real constant, and we suppose that an is not equal to 0. It is a nth order difference. If we take nth order difference, divided difference of fpx, we will get the constant value an, and if we take the n plus 1th order of px, then we will get 0. Now, dear students, please write down the relationship between the forward difference delta and the divided difference delta. Of course, for equispaced exercise, this will be very helpful to you in our future calculations.